So in this video, we're looking at the derivative and the tangent line problem. So, tangent line problem. Basically, calculus grew out of four different problems that the European mathematicians were working on during the 17th century. These four things were the tangent line problem, the velocity and acceleration problem, min and max problem, and the area problem. Now, each of these problems involves the notion of a limit, and calculus can be introduced with any of these problems. And what does it mean to say that a line is tangent to a curve at a point? Now, essentially, the problem of finding the tangent line at a point really boils down to just finding the slope of that line, right? You've got a point. What you need is the slope to actually give you the equation of the line. So you can approximate this slope using a secant line. We talked about this back in chapter 1. So if we look at the point of tangency, the point we'll call CF of C, and some secant point, which can be found by just adding that delta x, that change in x, to our C value. So you have C plus delta x, and then, of course, f of C plus delta x for your second point. Now, or your y value. So if that CF of C, so this is just the x and the y, for the point of tangency, right? C and f of C, and then C plus delta x. And this is the, we'll call this x1 y1, and this is x2 y2, right? So we're talking about this is the point of tangency and some second point, some random second point. Now, the slope of that secant line through these 2 points is given by this slope formula, y2 minus y1 divided by x2 minus x1. That's your standard slope formula from pre-calc. Now we're going to change this into m of the secant line. So we're calling this the secant line. So f of c plus delta x, which is y plus 2, or y2, minus f of c, which is y1, c plus delta x, which is x2, minus c, which is x1. And this is just a simple substitution, right? After we cancel the c's out, look at what we've got. F of c plus delta x minus f of c over delta x. Yeah, there's your difference quotient, right? Knew it was going to pop back up. Now, that delta x, that denominator, that represents the change in x, and that f of c plus delta x minus f of c, that represents the change in y, right? The slope, y2 minus y1 over x2 minus x1. So we can get a better and better approximation, or a more accurate approximation of the slope of that tangent line by choosing points that are closer and closer to the point of tangency. So if we move this point down, right, if it gets closer and closer and closer, it looks like we're moving the delta x up, right, which is what we're doing. Because here, this is the point of tangency. So we're taking our point and we're moving it closer, closer, closer. And notice that that delta x, the amount that we're adding to c, is getting smaller and smaller. Well, at the point of tangency, what's that value of delta x? Yeah, that's 0, right? So this is basically a limiting process where we're taking the limit as delta x approaches 0. So this is how we're going to define the slope of the tangent line, okay? So if f is defined on an open interval containing c, and if the limit exists, the limit of delta y over delta x, then the line passing through CFC with a slope of m is the tangent line to the graph at that point. So it's important that we recognize that we're just going to call this the slope of the graph of f at x equals c, right? Now, remember, this is at x equals c. This is not anything to do with this. This is delta x approaching 0, right? This is that change in x getting smaller and smaller and smaller. Now, to find the slope of the graph of f of x equals 2x minus 3, when c equals 2, and we say the slope of the graph, but we're talking about the slope of the line tangent, right? So we're looking at f of x plus delta x minus f of x over delta x, or delta c, sorry. So we're given the c value, right? So this is f of c plus delta x minus f of c. So we're talking about plugging 2 plus delta x in, so 2 times which is 2, sorry, minus 3, minus plugging 2 in, 2 times 2 minus 3, all over delta x. All right, and this is the limit as delta x approaches 0. So we're going to distribute. We're going to get the limit as delta x approaches 0 of 4 plus 2 delta x minus 3. We're going to distribute this minus 2 times 2, which is minus 4, and then plus 3. And remember, when we do a difference quotient, we know these should cancel out, right? All the last terms should cancel out, and you're just left with the limit as delta x approaches 0 of 2 delta x over delta x. Those cancel out, and we're just left with the limit of a constant, which is just the constant. So the slope of that line tangent to that point at c equals 2 is 2, which makes sense because we know that this is a line, and we know that the slope of a line is 2, right? So we don't have to worry about that. We know that any point of tangency on a line is the line itself. Now, the definition of a tangent line to a curve doesn't cover the possibility of a vertical tangent line. So for these, you can use the following definition. If f is continuous at c, and the limit equals infinity or negative infinity as delta x approaches 0, then that vertical line x equals c is, then the line x equals c passing through c is a vertical tangent line. So if we do these limits and we get either infinity or negative infinity, then we know that it has a vertical tangency, okay? So here's a function, and we can say it has a vertical tangent line, because notice that it has it's what we call a point of inflection, which we'll talk about later, but right now we can see that I can't draw a line like this because it may be tangent here, but it's going to be secant. And no matter where I go, it's always going to be crossing two lines unless I go straight up and down. So that's vertical tangency. And when the domain of f is the closed interval from a to b, you can extend the definition of a vertical tangent line to include those endpoints by considering the continuity and the limits from the right and from the left. This is kind of what we talked about with taking limits, right? We can't take the limit of a closed interval because it has to approach the same value from the left and the right. So what we will say is we can extend that vertical tangent line to include those endpoints if we look at it from the right and the left, and we talk about the continuity and the limits there. So we're talking about those right and left hand limits. So if you have any questions about the tangent line problem, go ahead and shoot me a remind or make sure and ask a question in class.